Hi friends, let's continue our series on explaining Kahn's algorithm. So in this video, we're going to look at problem 2050, parallel causes 3. In this video, we're going to point out the difference of this problem with problem 1136. So the main part of the two problems are both Kahn's algorithm, but here we need to count the minimum number of months needed to complete all the causes. So in other words, besides the main Kahn's algorithm, we need to have a way to do the effective counting. So for this, actually, we're going to use some idea like dynamic programming. So another difference for the current problem with problem 1136 is that so here the test cases are generated such that it's possible to complete every cause. In other words, the graph is a directed acyclic graph, or in other words, there is a valid topological sorting. So here I will not go over the full statement, but I want to mention again. So here we have n causes, and those causes are labeled from 1 to n. In other words, it's one indexing, right? So there's another thing that is time. So time I will denote how many months it takes to complete cause I plus 1. So here there's the index I, and here is I plus 1 cause. So this is due to that, due to the fact that when we do the indexing for a list or array, so we're using 0 indexing, right? So well, here we assume that we use 1 indexing. So we need to keep this in mind when we do the coding. Though this is some small details, it's important to notice that, right? So here, the number of causes is bounded by this number. This is a large number, right? And all the pairs are unique. And lastly, the given graph is a directed acyclic graph. So with that said, we are ready to look at the coding. So for this problem, the main thing is how we do effective counting of the times. For example, in example 1, we can simultaneously take causes 1 and 2, but causes 1 takes 3 months. So in this level, we're going to use 3. And then we have 5, so 3 plus 5, that will be 8. This is the return. And in example 2, so we can simultaneously take causes 1, 2, 3. So here 3 takes 3 months. So for this layer, we are going to use 3 months. And after we took these 3 causes, we can take cause 4. So it's going to cost us 4 months. So we're going to have 3 plus 4, that is 7. Then we can take the remaining one, that is 5, using 5 months. So in total, the minimum number of months we need to is 3 plus 4 plus 7. So in other words, this is a path corresponding to the 12 months time. So with that said, we are ready to do the coding. And in between, we're going to expose to you the logical details. So let's first recall in Kahn's algorithm. So there are 2 ingredients. One is traversal, one is in degree, right? So the traversal is initialized by the in degrees, right? The first thing we want to do is, let's see, we have in degree. So I'm going to use this, right? So 0. So here I'm going to, for I in range, I will write n, right? Basically, I want to represent the causes using 0 up to n minus 1. So we will adjust this, and then we just need to adjust the here. The i's cos I will be corresponding to time I in this way, right? And also we want to have a graph, so we can use this. So I set for I in range n, right? So this is the preparation step. And next, we are going to build the graph according to the relations. So for start, end in relations. Then the graph S will be the prerequisite for E, right? In other words, E is a neighbor of S, a direct neighbor. And also I'm going to update the in degree, because we have used the zero indexing, so we can do graph e, so e minus 1 equals let's see, graph let's see here. I guess we need to do this graph s minus 1 add e minus 1, right? Because s and e is in the range from 1 up to n, but here, because of our indexing, they are actually in the range from 0 to n minus 1, right? So the in degree will do in degree of this cost will be added, incremented by 1, right? So with that done, basically we finished the preparation step. So next, let's first get the source for multi-source depth first search, right? So I'm going to use deck collections. So deck. So here, let's use maybe use list comprehension, right, for node, and for degree in degree items if degree equals 0, right? So now once we have this part, and also we need to in order to do the compute the time, I'm going to initialize a result. So this has a length n. So basically result I will be the time to finish causes I, right? So here I'm going to make some initialization. So for cause in deck, for those cause, so we can directly finish. So for example, this 1 and 2. So 1 use 3 months, 2 use 2 months. So what we are going to do is result cause equals time cause. So this we finished the initialization. Next, what we want to do is the traversal, right? So this is basically the main part. One is in degree for the Kahn's algorithm. The other is traversal. Here we can see it's a multi-source breadth first search. And then first, this is a very standard well queue. This is deck or queue anyway. So we use the queue behavior actually. We get the cause, that is deck. So we are going to use the pop left function. So for this cause, we are going to check its neighbor. So for neighbor in graph cause, then if we first update the time, the result time is like this, right? So result the original state, and then the time or the result for cause plus time we finish the neighbor, right? Then this is actually due to the current problem logic. And if we do not include this row, and the other part will be standard Kahn's algorithm. So in degree of the neighbor will be decremented by 1, and then we check its in degree if it's 0. If this in degree is 0, it means that for this neighbor cause, all the prerequisites are finished. So in this way, we can enqueue to the deck. So append the neighbor. So once we done this, by the problem assumption, so we can always finish all the causes, right? So we just need to return max of this result list. So before we make any comments, let's first do a test. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes the generic case. So here, let me first comment. If we do not include this part and this line here, so this will be the standard Kahn's algorithm. And so the difference of the current problem with problem 1136 is the computation or the return. So for this problem, specified to the logic here, so that's the corresponding part. If you delete all this part, it's the standard Kahn's algorithm. So I hope that you have a clear idea about Kahn's algorithm and about the application with the specific problem logic here. With that said, I guess that's about it for this video. You are welcome to follow up other videos for Kahn's algorithm. Thank you.